to review the bending, we know that theta is the angle in radians. All right? And we know omega is the angular speed, which is in radians per second. That's how much this is changing over time. So let's just write that in. Okay? All right, so it's a lot like velocity. And then, look what happened. And we know that v, the velocity at anywhere on this circle, is equal to r times the angular speed, how fast it's rotating. Ooh, look what's happening here. It's speeding up. It is speeding up, speeding up, speeding up, speeding up. So that means if omega is changing over time, what do we got? You got it. We got an angular acceleration. And this is what is known as angular acceleration. All right? Angular acceleration is easy. It's little alpha, and that is equal to the change in omega over the change in t. And we're going to consider it to be constant. We'll consider it to be a constant for our purposes in this class. That omega is going to stay constant. So therefore, what do we know about a constant acceleration when we're going in a line? Well, we know this, that the distance, so here's for displacement linear, and here's for displacement angular. Okay, we've got displacement linear, we've got x is equal to x final minus x initial. Here we've got theta is equal to theta final minus theta, or change in x, is equal to theta final minus theta initial. All right. Oh, I put it as equal to that. Yeah. Okay. And we also know this, that v is equal to the change in x over change in time. V omega here is equal to the change in theta or the change in time. They're analogous to each other. This is the velocity, straight line velocity. This is the angular speed. Okay, and we know that the acceleration is the change in velocity over the change in time, and this is the angular acceleration is equal to the change in omega over the change in time. All right, so everything stays consistent. We're just going around in a circle. All right, and we also learned that v equals r times omega. All right, so let's do a problem then. So let's say we've got a helicopter blade. So we're looking at the top. I'll just show you the problem right here. Let's just read it together. Okay, let's zoom in. Read this problem together. So here it goes. A helicopter blade has an angular speed of 6.5 revolutions per second. Okay, revolutions per second we'll take. It's not radians per second, but we can change that to radians per second if we want. And it has an angular acceleration of 1.3 revolutions per second squared. Hey, it left it in the same units, revolutions instead of radians, so that's fine. So we'll just leave it in revolutions. Find the magnitude of the tangential speeds and the tangential accelerations. All right. Okay. So at that very specific time, and it's got a radius. Oh, they want us to change it to radians per second. Okay. Oh, we're going to have to change it to radians per second because we need to find the tangential speeds and tangential accelerations. All right. So we got this. We know that r. I know that. Oh, let me decrease this a little bit. It's a little bit too scary. Scary big there. All right. So we know this. Omega, 6.5 revolutions per second. Alpha is 1.3 revolutions per second. That's a lot of, that's moving pretty quick. Moving pretty quick. All right. Now, we want to know V, and we want to know A, tangential. In other words, going back to my picture here, this thing is going to speed up. So right at this juncture, it's also got a tangential acceleration that's going this way. All right. Hopefully but that tangential acceleration on the edge is going to stay the same. But the velocity, since it does have a tangential acceleration, the velocity is going to get going faster. Okay. So what's that look like? Well, first of all, we've got to change this to 6.5 revolutions per second times 2 pi divided by 1 revolution. There we go. So omega (40.8 radians per second). And so the velocity at that point, since the radius is 3 meters, it did show the picture that it was, where r is equal to 3.0 meters, then v is equal to r 3.0 meters times 40.8 radians per second. I don't need to multiply that out, but you can see that it's very fast. Now, here you go. The acceleration, the tangential acceleration is a little bit different. No, it's not. I was thinking something else. I'm sorry. The tangential acceleration is equal to this. It's equal to r times alpha. That's the tangential acceleration. All right? So, when something is going around in a circle, they gave us what we per second squared. I messed that up. All right, so we got to do the same thing again with that. 2 times pi times 1.3. So he hits 1.2. Close enough. Let's just round it up a little bit. It's clear. Sorry. Oh my God. I think I want to go on spring break about as bad as the students do. There we go. So alpha in radians per second squared is equal to 8.1 radians per second squared. So the tangential acceleration is equal to r 3.0 times 8.1 radians per second squared. That's pretty fast acceleration. All right. I'm going to stop.